Hello, this is Aveek and welcome back to my channel. So in this video, we are going to see how to draw the shear force and bending moment diagrams for a UVL, that is uniformly varying load. In my previous videos, we have seen how to draw the SFD and BMD for point loads and UDL, right? So solving this kind of problems, that is UVL, we have to apply a different approach. The basic concepts will be same, but we will be applying a different approach for solving the UVL. So we are given a UVL where in the leftmost we have a support, that is a roller support, and in the rightmost we have a pinned support, or we can say hinged support, right? So we already know that in case of a hinged or a pinned support, we have two reactions, right? One is in the vertical direction, let it be my RB, and one is in the horizontal direction, so let it be my XB. Okay, and for a roller support there is only one kind of reaction, so it will be vertical, it will be in a vertical manner, so it will be RA, right? So why this concept of supports I have explained in my first video, so you can check that out. Okay, now the thing that we have to do is to calculate the values of these reactions. So for that we'll be using the equilibrium equations, right? So see, firstly the value of XB will be 0. Why so? Because there is no other force to counterbalance or acting in the horizontal direction. So we can say directly that the value of XB is nothing but 0. Okay, now let us find the values of RA and RB. So for that we will apply this one, that is the summation of forces in the vertical direction will be 0. Okay, so RA and RB both are acting upwards, so positive, and this will be counterbalanced by the forces which are acting downwards, that is the UVL. And guys, what is the value of UVL? How do we find the values of UVL? For finding the values of UVL, we have to calculate the area of this. Okay, so the area will be half base 4 and height, that is this, right? Okay, and this value of UVL will be converted into a point load, and which will act in the centroid of this UVL. So C is the centroid of this UVL, and the value of this, that is half into 4 into 12, is the force which is acting in this centroid, right? And what is the location of centroid in case of a triangle? It is one third before the base, right? So it will be here. Okay, so let us just simplify it a bit. So it will be RA plus RB equals to 24. Let it be my equation number 1. So here we have two unknowns. Now we have to find the values of RA and RB individually. So for that we can do one thing, we can calculate the moment about this B. So the moment about this B will be nothing but 0, right? So what are the forces acting first? So before that I'll be telling you that I'll be considering the anti-clockwise moment as positive and the clockwise moment as negative. So see guys, this RA will produce a moment of in a clockwise sense, sorry. So in a clockwise sense, right? So it will be negative RA. So this is the force. What will be the moment? RA multiplied by the perpendicular distance. So it will be RA into 4. Now see, now this one, that is C, will try to will create an anti-clockwise moment. So this will be positive. So what is the magnitude of this force acting on the centroid? It is nothing but 24. Okay, and what is this distance? This will be 4 into 1 by 3, right? So this will be 4 by 3. It will be equals to 0. So if you calculate the value of RA will come out to be 8 kilonewtons. Just put this value here. So we'll get the value of RB, that will be 24 minus 8 minus 16 kilonewtons. right? So we can write these values over here. That is RB will be minus 16 kN and RA will be 8 kilonewtons. Okay, so I hope this thing is clear. So now let's try to calculate the shear forces and the bending moments. So for that, you already know that I have to consider a section. So let me consider this section. Okay, so let this section be X and X. So I'll be drawing the FBD, the free body diagram of this section. So I have considered section A, B, right? So how it will look like? It will be like this, right? This is my XX, okay, and let us say this is my A. So let us say this section is at a distance of X from the origin, and here A is my origin. Okay, so we have a reaction over here, RA, the value of which we have got to be 8 kilonewtons. Okay, and this is, we have UVL in this, right? We have UVL that is acting here. Okay, so what will be the total value of this UVL? It will be the area of this particular triangle, and it will be acting it will be acting in the centroid of this very triangle. Okay, so we have to find the value of this. So the shear force will be in the downward direction. I hope the sign conventions are clear, and the bending moment anti-clockwise. Okay, so by now I guess you are familiar with this. Okay, so let us calculate the shear force. So Fx, so see, the value of Fx will be 8. 8 is acting upwards, right? So 8 is in the upward direction, so let it be positive. So 8, and what else we have? We have the value of this which is acting in the downwards. Okay, so negative. So one thing, guys, to find the magnitude of this force, that is the total value of this UVL over here, we have to calculate the value of this area of this triangle. So what will be the value of this area? Half into X into this length, right? So how do you find the value of this length? We can find the value of this length by using the similarity of triangles that you have learned in your class 10, right? So we used to have Thales theorem, if you remember. So let me be my total UVL. So let it be my total UVL, that is this very thing. Okay, so it will be positive, sorry, 12, and this value is 4, and let us say this section is somewhat here. Okay, this section is somewhat here, and let me consider this length as my Y. Okay, and this length is X, that is this one. Okay, so this is my X. So by Thales theorem, what we can write? So let me write this. By Thales theorem, we can write X upon this very length, that is 4. So X upon 4 equals to Y upon 12. Equals to Y upon 12. So if you need the value of Y, right? So if you just subject Y, you will get 3x. Okay, this will get cancelled with 3, so Y will be equals to 3x. Okay, so what will be the magnitude of this force which is acting downwards? It will be half into base, that is x, and height, that will be 3x. Okay, so I hope this is clear. So now what else? Now we can write Fx equals to 8 minus, so it will be 3 upon 2 x square. Okay, so we first need the value of shear force at A. So let me find SA. So see, guys, the value of shear force depends upon the value of X. Okay, that is the distance from the origin. So accordingly we have to put the values. So for finding the value of shear force at A, the value of x will be 0. Why it is so? To calculate the value of shear force at A, just compress this load. Okay, so at A, the value of x will be 0, and as you go through this beam, just increase the value of x. So at point B, the value of the x will be 4, right? Okay, so at A, value is of x will be 0, so just put here 0. So SA will be, okay, I have written F over here, so let me just write S. Okay, it's the same thing, shear force, nothing else. Okay, so SA will be, if you put here 0, so this part will become 0, so SA is 0. And SB, the value of shear force at B, x will be equals to 4, so you put here 4 and you'll get minus 16 as your shear force at B. Okay, now what else? So see, the value of shear force at A will be 0, and the value of shear force at B is also is minus 16. Sorry, is minus 16. That will be something somewhere here. So let it be here. This is my minus 16. Okay. Now the question that arises is that how. Okay, one thing I did a mistake, guys. It will be not be 0. This term is 0, so the value of XA will be 8. Sorry, very sorry. So this will be 8 kilonewtons. Okay, so the value of shear force at A will be somewhere here. Okay, fine. Now the question is, how do we join this line? Okay, so for that, remember one thing. In case of UVL, for joining this line, you have to find the point where the value of shear force becomes 0. That means at the point where the value of shear force becomes 0 will be the very point where the value of bending moment will be maximum. Okay, so in my first problem that I solved, I guess I have discussed the point of contraflexure. Okay, so what is the point of contraflexure? The point of contraflexure is a point on the beam where the value of the bending moment becomes 0. Okay, and here we have to find the value of the point where the value of shear force becomes 0. So basically the point where the value of shear force becomes 0, that very point is called as the inflection point. Okay, so here we have to find the inflection point. So let us find it. So I have told that the value of shear force at the inflection point is 0. So one thing we can do is we can equation this shear force equation with 0, right? So we can write Sx equals to 0 for finding the inflection point. Okay, that means 8 minus 3 by 2 x square equals to 0. So if you calculate this, the value of x you will get is 2.3 meters. So we can say that at the distance of 2.3 meters from the origin, so this will be something in the between, that is 2, and here will be my 2.3, let's suppose. So we can say at the value of 2.3 from the origin, the value of the shear force will become 0. So now we can join this line, but how do we join this line? So for that, just check the degree of the polynomial, the degree of the polynomial of the shear force, that is x square. We have x square. Okay, so this will be joined by a parabola. So you can join it like this. Yes, so here in this section we have, in this part we have positive shear force, and here we have negative shear force. So the drawing of shear force diagram is complete. So now let's calculate the bending moment values in this for this particular UVL. Okay, so for calculation of bending moment we will consider this same diagram. So see, bending moment I can write it as mx. So I will apply the hogging sagging approach. We know that if a beam sags, it will be positive, and if a beam hogs, it will be negative. Okay, so at point A, this 8 kilonewton force will try to sag this beam. Okay, so that is try to bend this beam this wise, in this manner. Okay, so it's positive, so positive 8 into what will be the value of the moment, that is the perpendicular distance, 8 multiplied by the perpendicular distance, that is x. Okay, and what else we have? We have this force which is acting downwards, so it will try to hog the beam. So the sign convention is negative, right? So what will be the value? So the value of this is what? The value of this is this one, half into x, that is 3 by 2 x square. 3 by 2 x square. This is the value of the force. And what will be the value of distance? That is this value. What will be this much? So we know in case of calculation of centroid, it is 1 by 3rd before the base. Okay, so it will be into x by 3, right? As simple as that. So if you calculate this, this will be 8x minus x cube upon 2. Okay, now what? Now you have to find the value of bending moment here. So for finding the bending moment at A, we will put x equals to 0. So every term will become 0, so the value of bending moment at A will be 0. Now the value of bending moment at, so this point, let this point be, this is my A, this is my B, let this point be D. Okay, so now let's find the value of bending moment at the inflection point, that is MD, where the value of x will be 2.3. so if you put 2.3 here and 2.3 whole cube upon 2, you will get the value of MD as the value of MD you will get is 12.3 kilonewtons meter. So guys, one thing to note is this is the value of bending moment at the point of inflection, right? Where the value of shear force is 0, means the value of bending moment is maximum. So this MD is nothing but the bending moment, that is the maximum bending moment. Okay, so just keep this in your mind. Now finally we have the value of bending moment at B, where we will put x equals to 4. So see, if you put here 4, so 8 4 is 32, and this is 4 cube upon 2, that is 32, so it will be 0 again. Okay, so the value of bending moment at A is 0, the value of bending moment at B is also 0, but the value of bending moment at D is the maximum, that is 12.3. so let us suppose, so this is 8, so let us suppose it is somewhat here. Okay, it's not accurate, so let us suppose it's somewhat here. So this is my D, and this is 12.3 kilonewtons meter. So now the question is, how do we join this? So for that you have to check the degree, that is 3, it's a cubic polynomial, so we will join it using a parabolic curve. So this will be somewhat this, like this. Okay, it's not so precise, but okay, fine. Okay, so this is our maximum bending moment, sorry, and the whole bending moment, the bending moment across the beam is positive. So this completes our SFD and BMD on this UVL, that is uniformly varying load. So I hope this video helps, and please do subscribe to my channel to show your support, and more videos are coming on shear force diagrams and bending moment diagrams. So thanks for watching.